Hello everyone, I am Sumit Suman presenting my PhD thesis titled Empirical Methods for Structural Risk Minimization. The problem statement addressed in the thesis pertains to the notion of minimizing risk in training machine learning models, which affects the generalization ability or the performance on a test set. Risk could be empirical, which measures how well the model has learned from the training data, or structural, which measures the risk due to model selection. In cases where the data available for training is low, which is common in medical, healthcare, and life sciences applications, structural risk minimization becomes important to develop low complexity models that generalize well. This thesis focuses on approaches to minimize structural risk by developing approaches to minimize the VC dimension. This slide shows the approaches developed in the thesis for minimizing structural risk. The minimal complexity machine, a learning model which minimizes VC dimension and results in sparse, generalizable models, has been developed for the extreme learning machines. Results on the MC-ALM show improved generalization and sparsity in the trained networks. A quadratic variant of the MCM, which minimizes a tighter bound on the VC dimension, called the QMCM, has been developed for classification, regression, and feature selection settings. A scalable version for large datasets using stochastic subgradient descent has also been developed and evaluated. Another model with derivative constraints called the MCM derivative makes such models amenable for training with extremely low training data settings. Lastly, EigenSample, an approach for additional sample generation and that allows for parameters to control the quality of the generated samples, has been developed and evaluated for classification and regression settings, including a non-iterative least squares version. The details of all models can be found in the publication links provided here. The methods proposed in the thesis have resulted in various applications and extensions illustrated here. These include twin neural networks for class imbalance, neurodynamical systems for hardware realization, and SGD-MCM scalable to large datasets. Published work also includes applications to classification of biosignals such as EEG for motor imagery and surface electromyogram for hand gesture recognition, apart from other applications in the healthcare domain where class imbalance and low training data are impediments to building generalizable learning models. Thank you.